Okay, so I want to keep looking at 3D vectors and some applications of that cross product. And so maybe there we go. Okay. And so then another one of the applications of a cross product, besides being a vector that's perpendicular to two given vectors, is this idea that cross product is actually going to help us define an equation of a plane. And the equation of the plane is based on a perpendicular vector called a normal vector. So when I see this word normal vector, right here. So when you see the word normal vector, that's another way to describe a relationship that's perpendicular. And usually it's reserved when you have a vector, which is like a line segment or array, and then a plane. And so if I just think about if I could somehow like represent like this idea of a plane. So like try to draw this like 3-dimensional, or the surface, right? So here's a plane, and if I have a vector that's perpendicular to that plane, so then it's perpendicular, if I think about it like that, it's coming like either straight off the page, or like maybe it could also be going like straight down the page. But that's what's called a normal vector. And there are lots of ways to define planes. The way we're going to define planes in this particular unit is based on, well, what are the coefficients of that normal vector? Because if you know what the coefficients of that normal vector are, they are the same coefficients as the plane. And the language that changes, or the difference that changes, is that when you're dealing with a vector, notice your vectors are i's, j's, and k's. That tells you that you're in the language of the vector. So that would be the part that's coming off the plane over here. Or if you want to talk about an equation of a plane, and a plane has, if you think about like this point right here in space, has an x component, a y component, and a z component. So if you're talking about the equation of the plane that has all of those points that satisfy, like, say, a certain condition, then they would have to have an x, a y, and a z. And so that would be just a generic equation of a plane is some coefficient of a, x, plus some coefficient of b, y, plus some coefficient of c, z, plus d equals 0. So it's kind of like a line, which is like ax plus by, but then it's just like one extra element, or one extra dimension, the z dimension, because it's, there's 3 components. So we will define planes based on that normal vector. And sometimes you are just given a normal vector. Like this problem number 2, it says, hey, here is the normal vector. And so this particular question is more of a vocabulary question, just saying, do you realize and recognize that a normal vector is the same coefficients as the plane? So if they tell you what the normal vector is, you can pick off that 3, call it 3x. You could pick off the 2, or I should say -2, -2y. You could pick off the 1, so plus 1z, and those will be the first 3 coefficients. But now I need to get through this point. So we don't know what our intercept is, our d element, so to speak. So what we have to do is actually substitute 3, -1, 5 in for x, y, and z, and actually solve for this d value. So there's not a lot of work to do here, other than recognizing a vocabulary lesson, or a vocabulary word of normal. Normal vector means it's the vector that has the same coefficients as the plane. Normal does mean perpendicular, and that's how we're defining our planes. So we have 9 plus 2 plus 5 plus d equals 0 to find that intercept. Well, 9 plus 2 is 11, and 11 plus 5 is 16. So I would say that 16 plus d equals 0. So that means d is -16. And so then to actually answer this question, to find the equation of the plane, you go back and say, okay, oops, I thought I selected green. There you go. Say 3x minus 2y plus z. Now I know what my d value is, -16 equals 0. Now, sometimes students say, well, could you put the 16 on this side? Sure, that's fine, doesn't matter. But in terms of like a format, a lot of times you do just set it equal to 0. Okay, so that's like the fact that they gave us the normal vector, really there wasn't a whole lot of work for us to do. Okay, but now I'm kind of taking a peek at the next example. They don't give us a normal vector, but instead they give us 3 points that lie in this plane. And this actually can go back even to like algebra 2, where it says like, find a system of equations that, that basically all 3 points would belong to, because all 3 of these points have to go into some equation of a plane that has an x, a y, and a z. And so what we're going to do is use our knowledge of this normal vector being perpendicular. So this vector here, that we know that's perpendicular because that's what a normal vector is. And a normal vector has the same coefficients as the plane. What we're going to do is we're going to take these 3 points, plot them in our plane here. Like here's point 1, let's say, here's point 2, here's point 3. And the idea here is that if I can represent a vector that goes from one point to this point, and a vector that goes from one point to another point, if I could figure out, like if I write those 2 vectors and use some method, I don't know, maybe cross product, to figure out something that's perpendicular to both of those, that would give me the same coefficients that define the plane. So that's most likely how you're going to see this application. Find the equation of a plane that contains these 3 points. Okay. Now, it doesn't matter which way in terms of points which direction you go, but you want to make 2 vectors. And so I want to say, well, how do I get from this point to, let's say, this point? What takes me from point A to point B? So look at your x component. 3 went down a unit to 2. So it's just like a position vector. I call it -1 in the I direction. It went down 1. 4 goes all the way down to -1, so my j direction decreased by 5, so minus 5j. -1 up to 0 would be +1 in the k direction, so plus k. So there represents a position vector from this one to this one. Now, it doesn't matter the next vector. You could go from this one to this, or you could go from this one to this, or you could go from this one back to here, or this one back to here. It does not matter. But what I think I might do is I'll just go pick, let's say, this color. I'll go from this vector to this vector. Okay, so 2 down to 0, so that's -2 in the I direction. -1 up to 8 is +9 in the j direction. And then 0 up to 9 is also +9 in the k direction. So from these 3 points, and again, just thinking it from a geometric point of view, you have, here's your plane. Just draw a 3-dimensional plane. You have these 3 points, point 1, point 2, point 3. What we're doing is we're finding 2 vectors. Let's say 1 to here, and then maybe here to here. It doesn't really matter. So I found those 2 vectors. So then what I'm going to do is find the cross product of those 2, because that'll be guaranteed to be perpendicular. And whatever coefficients I have for that normal vector that's perpendicular, those would be the same coefficients as this plane. So it's kind of like that's kind of like the thought process. So I'm going to take these 2 vectors here and here, and I'm just going to really look at their coefficients. -1, -5, 1, and -2, 9, 9. And I'm going to do that process of finding the cross product. So I'm going to have to systematically kind of block out a column at a time. So the first thing I'll do is I'll block out this column here. So I have this 2x2 matrix left, and I'm going to find the determinant of that matrix. So -5 times 9 is -45. -45 minus 9 is -54. And that's in the I direction. Minus, remember, it's always the opposite. Oops, sorry. So cover this one up. So then we have -1 times 9 is -9 minus a -2. So -9 minus -2 is really -9 plus 2, so it's -7. Remember, it's already opposite, so then we make it a +7. That's in the j direction. And then we cover this guy up. And we do -1 times 9 is -9 minus 10, because remember that's a positive there. So -9 minus 10, which is -19. Minus 19. Okay. Now, those coefficients that I just found will actually be my coefficients when I get my equation of the plane that has like an x, a y, and a z, kind of like we did up in this example up here. But I just kind of want to check my work to make sure I did that right. Because remember, that vector that I just found, this cross product, should be perpendicular to both of those given vectors. And it's easy to check because we know that their dot product should be equal to 0. So if I take a look at my cross product, and I know the problem doesn't ask you to do this, so I'm just checking my work. But if I actually multiply this vector as a dot product with this vector, so let's just check our work, just to make sure, just so I can sleep tonight. So -54 times -1 is 54. 7 times -5 is -35, and then -19 times 1 is -19. So 54 minus 35 is 19, minus 19 is 0, so that's good. So most likely I did it right, but you could always check with the other one. -54 times -2 is 108. 7 times 9 is 63. -19 times 9 is 9 times 9 is 81. Carry my 8. 9 times 9 is 81. Carry my -171. And then good. 108 plus 63 is 171. Minus 171 is equal to 0. Okay, so I just want to check my work to make sure I had the right coefficients. Now I can just take those same coefficients and I'm going to switch out the letters. So instead of I, J, K, it's going to become X, Y, Z. So -54x plus 7y minus 19z. Now, because we're an equation of a plane, I have to solve for that d coefficient. And any of these 3 points satisfy it. You could pick any of them. It doesn't matter. And so I always try to pick like the one that I think is quote unquote like the easiest, like maybe the middle term, because 2, -1, 0 are relatively small. But you could have picked 3, 4, -1 or 0, 8, 9, doesn't matter. So let's say 2, -1, 0. So we have -54 times 2 plus 7 times -1 plus 0 plus d is equal to 0. Excellent. So then when we solve, that's -108 minus 7 plus 0 plus d. So that looks like -108 minus 7 is -115. So if -115 plus d is equal to 0, that means d is 115. So then my final answer, I have to go back in then and actually take this equation and actually put in what d was. So then I'd say it's -54x plus 7y minus 19z plus 115 is equal to 0. And again, you can check your work because any of the numbers should work, any of the other points. So let's say I pick 0, 8, 9. If I would have put 0 in here, plus 7 times 8 is 56, minus 19 times 9 was that 171, plus 115. Does that in fact equal 0? 56 plus 115 is 171, minus 171 is equal to 0. Perfect. Okay. So when they give you 3 points, like they just did here, then your job is to take any 2 vectors. It does not matter which position vectors you pick. There are 3 points. You choose 2 directions. It does not matter. They all will give you the same equivalent plane. Okay. Now, one thing I was actually just thinking about, like, let's say you picked a different order, you might get something that's equivalent to your plane. I was just thinking about that. So you might get something like maybe some people got an answer of positive 54x minus 7y plus 19z minus 115 equals 0. Like some of you maybe got that. And that actually is equivalent to this plane, just multiplied by a coefficient of -1. Maybe some of you got 108x minus 14y plus 38z minus 230 equals 0. That's another way to represent that plane. It's just multiplied by 2. So if you get something that's equivalent to the plane and you're just off by a multiple, then that's fine too. There's nothing wrong with that at all. Okay, let's do just one more example in this video, and then we'll pause and do another video. If you have two planes that are parallel to each other, so I'm looking at this next question here. If you have two planes that are parallel to each other, well, under Euclidean geometry, if they are parallel to each other, they don't intersect, which means that they have the same normal vector, because that vector would have to be perpendicular to both of them in order for those planes not to intersect. So again, it's more of a vocabulary. It's a check for, do you know this word? That if you know that the coefficients of this plane are the normal vector and the two planes are parallel, it'll have the same coefficients. So the first thing I'm going to do is I'm going to extract these coefficients and make it a vector. So now we're in the language of I and J and K. And again, not joking. That's the first thing that pops into my head when I say I, J, K. So I picked out 1 and a -6 and a 4. And now I know that those coefficients that define this normal vector of the first plane will also be the same coefficients, that same slope, the same direction of that second plane. So then I can just put it back into X, Y, Z. In other words, I didn't really need to do that other than just, I guess, theoretically, but now I need to pick a different intercept, a different D value, and this D value has to make sure I go through the point 3, 2, 1. So then if I solve for that, and I say, okay, that's 3 minus 6 times 2 is 12, plus 4 times 1 is 4, plus D. So make sure we go through this point. So that's -9 plus 4 is -5. Plus D is equal to 0, which means D is 5. So then this equation of the plane, so it will be parallel, but it will have a different intercept. It would be X minus 6Y plus 4Z, and we found D to be 5. Okay, so I think there'll be one more video of applications, and so same thing, like go through the module, take the little mini quiz, and then if you have any questions, certainly send me an email.